also mentioned that neutrinos play a significant role in the early universe, as did heat. What is their role exactly?
Well, in the sense of, so neutrinos are super duper light, like I
Right.
said, right? Um, so the energy kind of barrier you need to create them is quite small. The other thing is neutrinos don't have an electric charge, so the way they interact with like other stuff in the early universe is different than things that are charged, number one. And number two is that as the universe cools, you go from particles behaving in a relativistic manner because they're super, when things are really hot, things have high energy. If that energy is about the same order of their mass through this like E equals mc squared, then you would say the particle is relativistic, which means the kind of mechanics that it undergoes is like you don't treat it as a classical physics problem anymore.
Is that why it's beyond the standard model?
No, that's all within the standard model.
Oh,
That's not
okay.
anything fancy. That's like special relativity, like
Okay.
yeah, Einstein, 1905.
Okay.
um,
Oh, it's over 100 years ago.
yeah, it is over. It's crazy. But what neutrinos do in the early universe is essentially like as the universe cools, most particles become non-relativistic at some point, and neutrinos stay relativistic for a bit longer. So now you have this soup of photons, like regular light, and neutrinos, and there's so many of them, and the neutrinos do have mass, as we know, so they actually start to smear out to the clumping of matter. And depending on how quickly the universe's temperature drops, the mass of the neutrino, et cetera, you can sort of try to imagine like the universe is trying to clump together, but you have these neutrinos that are massive that are kind of smearing that out. So instead of having larger clumps, you kind of
They space out, I guess.
yeah, they space out. So I believe this is not my area of expertise, so like everything I say with a grain of salt. But I think you start smearing out like small scale structure formation, so like smaller clumps rather than larger ones, depending on how many neutrinos you have and also the energies at which they're moving relative to the universe's expansion, something like that.
And do they keep their energy levels kind of the same when everything cools off because they're so light?
No, they actually get, so when we observe them, like you have things in the universe are rapidly moving away from us, right? The further and further you look.
Well, aren't we moving as well?
Yes, but like the distance like between us is actually quite close on a cosmic scale. So we don't actually notice this. But and also there are other forces that are keeping us together. Like the Earth is a massive gravitational body that's attracting us. But when you look at cosmic distances and you try to see, well, you can see this with light. When you look at things further away, they get redshifted.
Yeah.
So it looks like the light is getting Doppler shifted as if something is pulling it away. This is not actually what's happening, but you can imagine this as like when you have a car coming towards you and it's honking its horn, it goes meow, and then it like drops in frequency as it passes you and it starts moving away from you. And that's a Doppler shift.
Okay.
But the horn is not actually changing its physical frequency. It's just the way the waves are hitting your ear that are coming in rapidly as the car is moving towards you, and then as it moves away, they're coming in more slowly because the car is carrying away some of that velocity. This is not what happens with light, but you can think of it in the same way.
Okay, that was a very good analogy, by the way.
Yeah, so as things are further away, they seem to be moving away from us even faster, so things get redshifted even more, and you can measure that. So the neutrinos from the Big Bang, in this sense, are actually very low energy if we ever see them, but they're predicted to be very low energy today. And actually the only source of non-relativistic neutrinos, as far as we can guess, in today's world would be neutrinos from the Big Bang, and there are experiments actually trying to search for those neutrinos themselves.
Are they in the three places that you mentioned, or are they elsewhere?
No, this is a different experiment called Ptolemy, and it's not even, I don't think it's even under construction.
Oh, okay, so it's brand new.
This is brand new. This is a proposal. I'm not sure. Maybe I'm wrong. Again, like I'm also,
it's okay.
I'm only human. I make mistakes, so please take everything I say.
This isn't your dissertation defense,
Yeah.